Okay, so we know what complex numbers are now. We know how to manipulate them as far as like arithmetic and taking roots and so on. Um, the next thing I want to try to understand is how functions of complex numbers look like. Try to visualize it and look at interesting things. Okay, in fact, the first thing that I want to try to move towards is trying to understand fractals. So you can see the flashy picture we have to the right. So that's an example of what's called a Julia set. Um, so to study Julia set, basically we have to understand quadratic functions in complex numbers. So some function where we square the complex number and then we add a complex number, some constant. Okay, so let's write down the definition of a function that I hope you've seen already. So a function f from a to b is a rule that assigns each element in the domain A exactly one element of the range B. So this is the name of the function, and what comes after the colon is the domain, and then arrow towards the range of the set. Okay. So let's kind of compare it to quadratic with real numbers. So if you're looking at it as function from real numbers to real numbers, quadratic functions are very easy to understand. We could just graph it, right? So x, this is the input axis. We plug in a number in for x. We square it and we add 1, and this is what the output looks like depending on different inputs that you put in. So graph is something that we take for granted, that kind of visually gives us what the function is doing at one glance. But there's an issue with complex numbers here. Complex numbers are two-dimensional. So if we're plugging in two-dimensional thing, and the output is also a complex number, so that's two-dimensional thing, to really understand what the function is doing, we need 4 dimensions, 2 input dimensions and 2 output dimensions. So there's a few different ways we can tackle this. One way is to break it up into real functions. So that's something that we could do. For example, so let's say we want to try to understand this function z squared plus 1. And we can write complex numbers as real part plus I times imaginary part. So we can kind of walk through what it would look like that way. So we square it. We do the usual FOIL. Keep in mind that I squared is equal to -1. And then collect like terms. So all the real terms are x squared minus y squared plus 1. And the imaginary parts add up to be 2x1. Okay. And we can kind of look at it in 2 parts. So let's say u of xy is the function that gives us the real part of the output, and vxy is the part of the function that gives us the imaginary part with the input xy. Right. So to understand one complex function, we could kind of understand it with 2 real functions, u and v, multivariable functions, because it depends on both the real part and the imaginary part. But the output is one-dimensional, right? So we could have pair of 3-dimensional graphs to try to understand this. That's one way to approach it. There's another way to kind of understand what's being inputted and outputted. And this is the tool that we're going to be using for pretty much the rest of the class. is to have like a before and after picture. So what we could do is we can look at what the domain looks like before we plug in the function. So let's say this domain is a picture of this word hello. I'm coloring it in because that's the possible input values, and try to deduce what the range looks like for that function. So you might distort it, you might stretch it, you might compress it, you might rotate it. It'll do lots of different things. But if you can understand this transformation or what distortion it kind of goes through, we can understand what the function is doing. Right? It looks like this function f is kind of stretching it and then maybe curling it towards the left. Roughly what the function is doing. Okay, so let's try to do this picture with the function z squared. So let's make it a little bit easier by not doing z squared plus c, but just trying to understand what the square function is doing. Okay, to understand the square function, it's easier to do it in polar coordinates. So let's do it. So if you have a function, the complex number z is equal to r theta, then when we square it, we square the modulus, and we end up when you square the exponential part, that doubles the angle. So we can understand in two different ways. The modulus of the output is square what it was before. Okay. And the argument of the output is twice the input argument. So those are the two things that the square function is doing. If we start with domain that looks like a circle of some radius r, after you square it, you get a circle radius r squared, right? Because that's how the modulus is transformed. On this circle, the modulus is fixed at r. The output must have the modulus of r squared. So that's what it's doing. Not only that, if you kind of imagine what the angle is doing, if you imagine z going around the circle radius r once counterclockwise, what it's doing in the output is that it's going through double the angle. So it actually wraps around the circle twice at double speed, double angular speed. So I hope that makes sense. Okay, let's look at a different shape. So we could draw lots of different shape, but maybe like a sector or a pizza shape. Okay, of angle 3 pi over 4. Okay, and let's say the radius here is just 1, just to make it simple. Okay, if the radius is 1, in the output, the radius is still 1 because that's 1 squared. But the angle from 0 to 3 pi over 4, it sweeps through double the angle. So if you multiply 2 to 3 pi over 4, we get 3 pi over 2. And that's going to be what the image looks like after the function is applied. All the angles are kind of doubled in that. I hope that makes sense. Here the angle is 0, so that stays on the positive real axis. And if you kind of look at all the intermediate angles, all these intermediate angles are those spokes that I drew should be double the angle of what it was drawn previously. Okay. And then if we try to understand something like z squared plus 1, So now we understand what the z squared does, right? It stretches the modulus according to z squared. Sorry, the modulus squared. So that's done. And also the angles are doubled, right? So that's what the z squared does. And then adding 1, that's kind of shifting everything to 1 unit to the right. Okay, that's like adding 1 in the complex sense. So every point is shifted to the right. I hope that makes sense. Okay, so now if you want to understand what z squared plus c is doing, it's z squared plus you'd shift in the complex numbers c direction, right? So if it was something like, if I'm adding c, which is 2 minus I, that would be shifting to the right 2 units and shifting down by 1 unit after you do the square transformation. Okay. All right. Another thing that we have to understand when we start to look at Julia sets is that we have to understand iteration of functions. So what I mean by that is if you have a function, we're gonna plug in a number into a function, and whatever output we get, we plug it into the same function again and again and again and so on. So let's pick a very simple function, z plus 1. So we're just adding 1 to the complex number. If we iterate this function twice, so that's f of z, the f of z is z plus 1, so I'm going to rewrite the input as z plus 1. And we're putting in the z plus 1 into the z, so z plus 1 plus 1, which simplifies to z plus 2. Okay, the third iterate would be f of second iterate of f of z, and we just computed the second iterate, so that's f of z plus 2. We plug the z plus 2 into the function and get z plus 3. Okay, if you've gone this far, I think most people can work out what the pattern of this iterate is. If we apply the function n times, that's the same thing as adding n to the original input. I'm sure most of you can take this pattern, and once you get the pattern, write down a proof using maybe induction. Okay. And this is the notation we're going to use. So if we put something in the superscript after the function name, in this part of the class, this means the nth iterate of f. I know it looks like we're doing nth power of f. So just to avoid the confusion, so if we have a function that we want to square, we'll write it this way. So to distinguish it from the second iterate of f. And when we look at the derivative of functions, we're going to use that parentheses to distinguish, like, how many times did we take the derivative. Okay. All right. So please maybe pause the video and then see if you can work out what the iterates of these two functions would be like. So the first function f is multiplying 2i to the input. What does the function look like if we do that n times? Or maybe z cubed. What would the function look like in that case? Okay, so we're gonna look at quadratic functions. We're gonna focus on them. So we're gonna look something like z squared plus some constant c. And we'll quickly see that this is not an easy thing. to compute. So just looking at a couple of iterates, if we square it and then add 2 and do that twice, we'll get some polynomial of 4th order. If we do that again, I didn't finish this computation because it's long, but it's going to be some 8th order polynomial. And because we have to cross multiply, this is not going to be an easy thing to work out after the 7th iterate or something. I think almost everybody would give up before that. We could say it's gonna be a polynomial, right? If you square a polynomial, we'll get a polynomial, and we add a constant to, we're gonna get a polynomial. And we know that the degree is going to be increased by power 2 each time. But I think that's the best I can get. Okay. So this is kind of a teaser what's to come. So when we study Julia sets, the polynomial of z squared plus c, we'll look at what happens to the iterate of this function. A lot of times these sequence will behave chaotically, whatever that means. And in doing so, we're gonna have to learn how to deal with sequences of complex numbers. Okay. In particular, we're gonna be interested in what happens to the nth iterate evaluated at 0, and hopefully make sense of taking the limit as n goes to infinity. Okay. And if we study that, we'll get a picture that looks like a fractal, the beautiful picture that I shared earlier in this video. So I think you have that to look forward to. Okay, this is where I'm going to end the video today. Bye.